techniques that I'm doing here would be applicable to biogeosciences. So the title of the talk today is to look at the data synergy and scaling effects of large sample multiphysics modeling using machine learning. Okay, so before I dive in, we do share our code here. It's recently updated, and I do have a Twitter profile where I interact with people often. So please come. All right. So before we look at the technical aspect, I want us to think about machine learning and think about it in the right context, right? So I often put up this picture here. I think because I think 100 years from now, when we look back, this would be a watershed moment where things really diverge. So this is the very classic battle between the very epic battle between AlphaGo and Lissido. And when Lissido lost the first game, Garry Kasparov, who lost to Deep Blue in the 1990s, can't wait to come out and say, condolences to Lissido, and I hope he can recover, but the writing is on the wall. And at the time, we think was still a fluke on the machine side. Maybe the next games would be different. The thing is, Lissido went down and lost the other two games, so he lost the whole set, but he won the fourth game, right? He won the fourth game using a talented, genius move that nobody saw coming. It was such a genius move that basically crashed the algorithm, right? It crashed the algorithm. And that turned out to be the first time humans won AlphaGo, and that also turned out to be the very last time humans won a game against AlphaGo. Because later on, AlphaGo went on and beat everyone out of the water. So it's beating every human experts 60-0. And all of these are top talents in the world, right? Top talents, and they were extremely smart. Ever after, nobody really think they can beat AlphaGo anymore. It's kind of a thing in the past. Really, it involves two convolutional neural networks, one neural network, one CNN, to kind of assess the strength of the game, okay, the strength of your position, the other to suggest a move. And you put the two networks together, throw it with the Monte Carlo tree search, and you got AlphaGo. You can code this yourself. You can train it. It's not that complex. But this game is very complex. Okay, the tree search complexity of the game is incredibly large. Okay, so if you think about the number of atoms in the universe, that's 10 to the 18 seconds power. The tree search complexity of the Go game is 10 to the 360th power. Okay, so we can't fathom how big that number is, right? So whatever you're thinking in your head is probably off, right? So this is an extremely complex game. So this really proves that this neural network can grasp very abstract ideas, very abstract and very complex ideas. And if you think, this is the first thing I want to convey, is that once these AI figure out how to figure out the right approach to solve a problem, we humans are almost goners, right? There's very little chance that you can beat an fully optimized AI system. The second is that it can grasp a very complex, very abstract ideas. If you think that your game, okay, your modeling game is complex, it's very hard, it's very abstract, think about this game. Okay, think about this game. All right. So I have another version of the title that would be gradient descent might be a better modeler. And that would be taken from this quote, gradient descent can write better code. And this is from Andrej Karpathy, who is the head of the autopilot system at Tesla. So he basically, the gradient descent can write better code than you, because they can optimize the system much better, right? So nowadays we're taking these machine learning algorithms to kind of in place of our conventional models, right? And it turns out in a lot of cases we examined, they do a better job. They do a better job than us modelers, than us modelers, just like they do a better job at playing Go game. Okay. Some of the examples that I've shown you, I'm sure some of you already know these, but maybe it's new for some others. This case study revolves around modeling soil moisture over the top surface, top surface. So we have a satellite that was launched in 2015. It goes around the world every 2 to 3 days. It senses the top surface soil moisture. The other case we did is streamflow modeling, where you have daily streamflow models. That's the runoff. And that you have accompanying attributes that are like the landscape, slope, soil texture, blah, blah, blah. There are also other cases that we did that involves dissolved oxygen and also water temperature. So we've done a whole rich set of problems applying this method called long short-term memory. Okay, so this long short-term memory, essentially the way these models are set up is you have atmospheric forcing data, that's weather data, right? Accompanied with these attributes, it's a static. They go into LSTM and they are trained to mimic something that you specify as the target of that system, right? And you train this system. It's basically a self-trained system that automatically learns what to input into the system, what to output, and what to forget. Okay? So it's highly adaptive. I am going to fly through a lot of these applications because this is not the focus of the talk today. I'm just going to spend very little time here, but if you're interested, you can look at these papers that we've done. So we've applied this system to simulate stream flow, including long-term projections and forecast, near-time forecast. We've got excellent results. We've got, this is where the traditional models are. This is where the LSTM models are. This is where you do a data simulation. You can use these deep learning systems to do data simulation. We get an NSC of 0.86 around for the United States, whereas the traditional model can get around NSC, nice coefficient of around 0.64. So there's a very visible separation. We apply the same problems for soil moisture, where for forecast, 3-day forecast, this is an error that's produced by a model, a method in the literature, and this is the error from us. And in this area, our error is almost 30 to 40% lower. And there's another application where you can use the network that is trained in a data-intensive region, and you can migrate it to a less data-intensive region. For example, you can train a neural network in the United States, but say for places like China and Chile, you don't have that much data, right? So you would think it's not applicable. These machine learning models may not be applicable. The thing is, you can train this model here and you can migrate it to these regions in a thing we call transfer learning. And after you do that, we find that the transfer learning models, in terms of the national subclinic coefficient, it's always higher. Okay, it's always higher than the local model. So you can sort of just borrow that information content from a data rich region and migrate to a data scarce region. It's sort of like you learn to play violin. Once you go and try to learn to play cello, it'll be a lot easier because it's kind of similar ideas, right? So there's a lot to borrow from. Another application is in terms of reservoirs, and we find these models can well capture the reservoirs. We have a 3,000 basin data set that says, okay, if you have a small reservoir in the system, that is actually extremely easy to model. Actually, if your reservoir can store less than about a month of flow, the machine learning can learn it very well, and it knows that this basin is very different from the ones that don't have a reservoir. And the difference, they're characteristically different because humans, change control the reservoirs. But actually, it turns out we can learn what humans want to do. So before the humans actually turn the knob, we know that humans are going to turn the knob at that time. If you think about it, it makes sense, right? The humans behave according to certain patterns, unless you go wild, right? And another application we apply to dissolved oxygen. It does a state-of-the-art performance. This is a paper published last year. We also apply it to stream temperature. It also does a very good job. Okay, so all these other applications, and what sort of the theme of the day is that there's a data synergy effect. And the data synergy effect. If you compare the global model, the models that are trained using all the data and the domain versus a local model, we find that this is the blue box. This is the local model is the red box. This blue model is the global model. The global model is always better than the local model. That means typically in statistics, you want to divide the areas into multiple regimes and fit one small model in each of these small regimes. It's a statistics 101. But with deep learning, what you want to do is you want to combine as much data as possible. That gives you an additional boost in the performance. Okay. All right, so considering time, I'm going to kind of move faster and really spend more time on this new application. Okay, in this new application, you know, the previous examples, we are able to simulate things that you can observe, right? Things that you have a lot of data for. But what about the variables that we cannot observe? What about evapotranspiration? What about groundwater and deeper soil moisture that you don't have a lot of observations? For them, we need these states so that we can support biogeochemical modeling, right? So a lot of the biogeochemical fluxes are also like this. You don't have direct observations for them. You have some observations of leaf area index, right? You have observations of other things. So in that case, is machine learning not applicable anymore? The thing is, it's still applicable, but in a different way. Here we're promoting that we move from parameter calibration to a new paradigm called differentiable parameter learning, okay, DPL, differentiable parameter learning. In this paradigm, we have a new deep learning neural network that essentially estimates parameters for your models. So because parameter calibration has always turned out to be a huge headache for hydrologic models, but I think also for biogeochemistry models, okay, ecosystem models. There are a lot of parameters there. So this network would actually estimate the parameters for these models. And these models then can output all the things that these models can output. So you're no longer constrained by observations anymore. Okay, so this is a whole system that we're training together. Okay, in this example, we calibrate the big hydrological model using SMAP data and this DPL scheme. Okay, there's a knowledge learning opportunities here. Okay, so just to show you what the test things that we've done, we think of one patch is a grid. This is a grid, right? So out of every 8x8 patch, we take one grid cell as our training grid cell. So on this, we will train a grid cell, you know, have the loss functions defined here. And we will test on these cells for a different time period. But we will also test it on a neighboring grid cell. Okay, this is on a neighbor here. So what we find there, this is an interesting figure. So if we compared this with the very, you know, standard shuffled complex evolutionary algorithm, and we calibrate them side by side, right? For this kind of calibration algorithms, you calibrate them here and calibrate them here and calibrate them here, and you use the kind of same parameters for the neighbors, right? So when you do that, you have the root mean squared error on the y-axis, you have the epochs on the x-axis. Here, one epoch means the model on average has been run once, one forward run for each grid cell. Okay. So see, for SCUA, it goes down this kind of a performance threshold of 0.05 in around 1,000 epochs. That's kind of what you expect when we have 7 parameters here. Okay. Again, these hydrological models are very similar to your column physics models. So very similar to your biogeochemistry models. Okay, so it's kind of the same thing. We have 1,000 epochs. But if I take one grid cell out of every 16x16 patch and train it, I can get down here in 300 epochs. If I train it over 4x4 patch, 8x8 patch, it goes down here by 30 epochs. And if I do this for every 4x4 patch, so the data become denser and denser, I go down this threshold in 5 epochs. So you see there's a data scaling effect here. Okay, it becomes more efficient as you have more training data. And actually the ending metrics, as you see, it becomes lower and lower. Okay, so altogether, this saves about 4 orders of magnitude in computation. So normally, for this job over the continental US, you need 100 processor CPU running for about 2 to 3 days. So for now, for this entire continental scale calibration job at S8, at 8x8 density, we need 1 GPU for 30 to 40 minutes. Okay, so that's a huge difference. And we get everything to be better. Okay, how is it better? I'm showing you here. The parameters that we get out of this is more spatially coherent. This is one of the parameters that we output out of this DPL algorithm. That it sort of agrees with the aridity, and that's what you expect for this parameter for Vic model. Okay, but if you look at the calibration, you see different parameters everywhere. This is a very famous problem of equifinality. Essentially, you can take different parts in the parameter space, and other parameters can compensate for it. So you could get all kinds of jumbled mess with the traditional side-by-side calibration scheme. But because when we applied our algorithm, we imposed one loss function over the entire US, it's able to give you that spatial continuity in that outputs. Okay, it is able to give you that spatial coherence. It's a much stronger constraint. Okay, so that leads to a range of benefits. Actually, so I might have deleted one slide, but we'll see it later. So that gives you a range of benefit. We compared this scheme, this DPL scheme, with traditional regionalization schemes. So regionalization is kind of sort of trying to do the same thing, but it's using human-based transfer functions. If you look at the CDF here, this is actually for hydrological modeling problems, and look at NSC distribution. The regionalization scheme for VIC for a data set gets about NSC of 0.32. Whereas with our scheme, you can get to 0.46. So there's a very material difference between these two guys. We compared it also with another. This MPR is called multi-scale parameter regionalization. It was a state-of-the-art scheme. Okay. There's another regionalization scheme, BIC 20. This is a different data set. This is a global hydrologic data set. Okay. For the median, they get an SE, a KGE is another metric that's similar to an SE in magnitude. It's about 0.46, but on that same data set, we can get to 0.56. So we get better spatial extrapolation. Okay, this is actually a prediction in ungauged basins test case. Okay, it's with a different hydrological model. So we've run different hydrological models for different data sets for different variables. Okay, and you observe this beautiful scaling curves. As you have more data, okay, this is a soil moisture case, okay, what we find is the ending metrics is this green line. This ending metrics gets better and better, okay. This extrapolation to the neighbor, so the extrapolation to the neighbor, that's this spatial extrapolation, this red line. The spatial extrapolation also gets better. So this is the line, and this is the axis associated with it. And this is from SCUA, and apparently that's much larger than what we have. We also compared with the uncalibrated variable, okay, evapotranspiration. This is correlation here. This correlation. Actually, when we have more data, our correlation becomes better and better as you have more data. It becomes what it means. We're getting the right parameters for the right reasons. The overall system is behaving better and better. Okay, so these scaling curves are very powerful. If you look at the stream flow cases that I just briefly described, as we increase the number of data basins for calibration, for training, you see this very sudden rises in the performance, and then it starts to kind of plateau, but it didn't saturate until even the highest density. So this is the phase where the problem, the network is trying to master the problem. It's trying to learn what this problem is about. After it learned, it kind of do some fine tuning. So what does this mean? Okay. You have orders of magnitude lower computational cost, but everything is getting better. It's like you're getting the economy of scale, but you also get a network effect. Everybody is now getting a better service. So how do you get this? How do you get this? The thing I keep saying is, all of our houses are similar. If I learned to fix my house, I can pretty much learn. I know already how to fix my neighbor's house, right? So there is commonality between these different problems that can be leveraged across. Okay, so these intricacies I learned here, I can just very easily migrate to my neighbors. So a lot of that commonality can be leveraged, and that is exactly what big data machine learning does. And that's what traditional paradigms don't give you that benefit. They don't give you this scaling effect. They don't give you this rapid mastering of the problem. Okay. So anyway, I'd like to end it here with a few minutes for discussion. So I think the conclusion is deep learning is gaining strength. That and it behaves very differently based on the amount of training data. The deep learning models prefer to see data with diversity and differences. It does not prefer homogeneous training data. Deep learning powered schemes may have a virtuous scaling curve, and this is the source of its power. Okay. We think that in the future, we're going to look at this very tight integration between machine learning and process-based models. And we can help the process-based models in many, many different ways. I'd like to end it here. Thank you.